Welcome back to Curious Orbit. In this explainer, we're diving into one of the absolute most chilling, awe-inspiring scenarios in the entire universe. I want you to picture what happens when a star encounters an invisible cosmic threat. Right? There's no solid surface to crash into, no giant impact crater, just this quiet, terrifying approach in the pitch dark. Imagine that star. It's been drifting peacefully through the immense void of space for billions of years, minding its own business. But suddenly, its path brings it just a little too close to a black hole. Now, in a normal stellar death, you'd probably expect a massive fiery explosion, right? Like a standard supernova. But here, there is no explosion. Instead, the black hole's gravity just begins its incredibly slow, destructive work, pulling at that doomed star in a silent, deadly grip. And honestly, that brings us to such a fascinating mystery. How in the world can something as enormous, as unbelievably dense and powerful as a star be completely destroyed by an object that's, well, totally invisible? What unseen force is physically capable of tearing apart massive stellar objects? We know the star doesn't just bump into a brick wall out there, so what exactly is pulling the trigger? Section 1. A fatal cosmic encounter. To answer that, we've got to look at the fundamental physics of this invisible weapon. So what is a black hole? By definition, it's a region of space-time where gravity becomes extraordinarily strong. I mean, mind-bendingly strong. This concentrated gravity is the invisible weapon I mentioned earlier. It doesn't need to be seen to exert absolute control over its environment. When a star crosses into this territory, it's stepping into a gravity well so incredibly deep that the normal rules of stellar survival, they just cease to apply. Section 2. The science of spaghettification. And yes, that's a real scientific term. Let's actually break down the mechanics here and see how gravity pulls off this destruction. As the star passes too close, the side facing the black hole experiences a much, much stronger gravitational pull than the far side. It's this uneven pull, this massive difference in gravity across the actual body of the star itself, that creates what we call tidal forces. As the star gets closer and closer, these forces become so overwhelmingly strong that they are physically capable of ripping the entire star apart. To really picture this in your head, just imagine pulling a ball of soft clay or dough from both ends. Instead of staying round, it stretches out, right? Well, a star caught near a black hole experiences this exact same phenomenon, just on a staggering astronomical scale. The intense gravity stretches the star's material into this long, super thin stream. It's an extreme process known as spaghettification. We can actually see this dynamic transformation broken down into 3 clear steps. Step 1, the star approaches the black hole, looking perfectly spherical and intact. Step 2, those overwhelming tidal forces take over, and gravity aggressively stretches the star, elongating it way past its breaking point. And then step 3, well, the star is no longer a star. It's been transformed into a superheated stream of matter, and a huge chunk of this material begins spiraling violently inward, straight toward the black hole. But here's where we hit another incredible question. Once the star is stretched into this crazy stream of superheated matter, does the entire thing just disappear straight into the void? Like, does all that material simply vanish across the event horizon forever, leaving absolutely zero trace behind? Section 3, a brilliant cosmic flash. So it turns out the aftermath of a star's destruction is anything but quiet, and it certainly isn't invisible. The crucial point here is that the star doesn't just fall straight in. While some material is definitely lost to the void, a massive amount of the stellar debris actually stays right outside the event horizon. This surviving material begins to rapidly orbit the black hole. And as it whips around at literally unbelievable speeds, these streams of gas crash and collide with each other. All this extreme friction causes the material to heat up to unimaginable temperatures, forming this unbelievably bright accretion structure around the black hole. As this stellar debris gets superheated, it releases enormous, and I mean enormous, amounts of radiation. This massive flash of intense light and energy traveling across huge distances through space is what astronomers officially call a tidal disruption event, or a TDE for short. So what started out as an invisible, silent ambush actually ends in one of the brightest, most violent flashes in the entire cosmos. Section 4. Detecting the invisible. Now, how exactly do scientists here on Earth actually observe these distant crime scenes? Well, because ordinary stellar activity is the norm, these violent tidal disruption events are actually incredibly rare. To find them, astronomers have to use modern surveys to patiently monitor enormous chunks of the night sky. They're looking for a very specific signature, a sudden, massive brightening coming from a distant galaxy that was, up until that moment, completely quiet. When they spot this sudden flash, kind of like the famous ASSSN 14Li event we observed back in 2014, they immediately investigate to see if a black hole is in the middle of tearing a star apart. And this brilliantly illustrates the reality of the situation. As researchers put it, it's like the universe briefly turning on a spotlight. You see, most massive galaxies have these huge black holes at their centers, but because black holes don't emit visible light themselves, they're incredibly difficult to observe directly. But when a black hole rips a star apart, that glowing accretion structure essentially lights up the black hole's hidden location. It makes the invisible, finally, visible to us. Now sure, we know these flashes look absolutely amazing through a telescope, but it raises a pretty vital question. Why are these spectacular cosmic disasters actually important to scientists? I mean, beyond just being this wild, violent light show, what real, tangible value do researchers get from watching a star die like this? Section 5. Why tidal disruptions matter. It turns out the wreckage of a destroyed star is actually a treasure trove of scientific data. It gives us clues about the universe that we simply cannot get anywhere else. These TDEs are literally a scientific goldmine. First off, they give scientists a super rare way to study those otherwise invisible, difficult-to-observe black holes. Second, the light radiating from the disrupted star can reveal vital information about the extreme, chaotic environment immediately surrounding the black hole. And third, over time, as some of that superheated material inevitably spirals inward, it helps astronomers investigate the exact mechanics of how black holes actually grow and consume matter. But, the exact outcome of this whole encounter highly depends on the black hole's mass. For what we call a massive black hole, the star gets torn apart outside the event horizon, and that's what creates that brilliant flash we've been talking about. But for extremely massive black holes, the gravitational pull is so immense and the event horizon is so unbelievably large that the star might actually cross the threshold and be swallowed whole before any visible disruption even happens. So no flash at all, just gone. This huge distinction is exactly why TDEs are so incredibly useful for studying different kinds of black holes. And this leads us to a really crucial piece of debunking. You've probably heard the myth that a black hole is just a giant cosmic vacuum cleaner that simply sucks stars in, right? Well, actually, scratch that. It's entirely false. The reality is far more violent, complex, and honestly, a lot more fascinating. A black hole doesn't suck. Its immense gravity stretches the star, tears it completely apart, heats the remaining gas through extreme friction, and then redistributes that material to create a brilliant, universe-spanning flash. In fact, the black hole ultimately only gains a fraction of the star's total mass. Every single tidal disruption event we witness is just this breathtaking reminder of the bigger picture. Our universe and all the galaxies within it, they aren't static. It's a highly dynamic, ever-changing environment. Stars move along their orbits, black holes grow in the dark, and gas shifts and changes. And sometimes, a star just takes a path that brings it a little too dangerously close to one of the most extreme objects in existence. Somewhere out there, literally right at this very moment, another star is making its final approach. And astronomers, they're just waiting for the light from that violent encounter to finally reach Earth. If you could safely watch one cosmic event from a spacecraft, would you choose a black hole destroying a star, a supernova, or a magnetar flare? Tell us your choice in the comments and subscribe to Curious Orbit for more space science and cosmic mysteries.